Hello, class. So this week we talked about encryption. We look at Microsoft Windows and encryption tools and technologies. And then our discussion went over encryption, and even the labs went over encryption. There was something very interesting that I wanted to share with you that is not in this week's assignments, but it is Shor's algorithm. And it's one of our concerns, because we use encryption every day in our communications. We use it in banking, we use it in our email, we use it when we're connecting to websites, any data transfers, business to business, we use it consumer to business. And so encryption's, embedded in almost all technologies. And even to the point, especially with Apple machines or Apple phones, even law enforcement is concerned that all communication is encrypted and they cannot access communications even with a warrant. And so but it is integral part of how our businesses operate today and how the world operates. So I wanted to share this with you. I'll put a link in. You can watch the entire video, but if you want to watch the beginning, it's pretty interesting.
The goal of encryption is to garble data in such a way that no one who has the data can read it unless they're the intended recipient. And the encryption of pretty much all private information sent over the internet relies immensely on one numerical phenomenon. As far as we can tell, it's really hard to take a really big number and find its factors using a normal, non-quantum computer. Unlike multiplication, which is very fast, just multiply the digits together and add them up, finding the prime numbers that multiply together to give you an arbitrary, big non-prime number appears to be slow. At least the best approach we currently have that runs on a normal computer, even a very powerful one, is very slow. Like, to find the factors of this number, it took 2,000 years of computer processor time. Now, it's not yet proven that we won't eventually find a fast way to break encryption just with normal computers, but it's certain that anybody with a large working quantum computer today would pose an immediate privacy and security threat to the whole internet. And that's due to something called Shor's algorithm. Well, actually it's due to quantum superposition and interference. They're just taken advantage of by an algorithm developed by Peter Shor, which I'm now going to attempt to explain. The kind of encryption we're talking about garbles or locks messages using a large number in such a way that decrypting or unlocking the data requires knowing the factors of that number. If somebody doesn't have the factors, either they can't decrypt the data, or they have to spend a really long time or a huge amount of investment in computing resources finding the factors. Our current best methods essentially just guess a number that might be a factor and check if it is. And if it isn't, you try again, and again, and again. It's slow. There are just so many numbers to check that even the fast, clever ways to make really good guesses are slow. For example, my computer took almost 9 minutes to find the prime factors of this number. So if you used this number to encrypt your data, it would only be safe from me for 9 minutes. If, on the other hand, you used a number like the one that took 2,000 years of computer processor time to factor, your data would definitely be safe from me and my laptop, but not from somebody with access to a server farm. This is similar to how putting a lock on your door and bars on your windows doesn't guarantee that you won't have stuff stolen from your house, but does make it take more time and more work. Encrypting data isn't a guarantee of protection. It's a way of making it harder to access. Hopefully enough harder that no one thinks it's worth trying. But quantum computation has the potential to make it super easy to access encrypted data. Like having a lightsaber you can use to cut through any lock or barrier, no matter how strong. Shor's algorithm is that lightsaber.
I guess that's a good place to stop. Since we got a camera.
Roughly speaking, to factor a given number, Shor's algorithm starts with a crappy guess that might share a factor with your target number, but which probably doesn't. And then the algorithm transforms it into a much better guess that probably does share a factor. There's nothing intrinsically quantum mechanical about this. You can, in fact, run a version of Shor's algorithm on a regular computer to factor big numbers. But perhaps unsurprisingly, the turning your bad guess into a better guess part of the process takes a very long time on a normal computer. On the other hand, this key step happens to be ridiculously fast on quantum computers. So our task is to explain how Shor's algorithm turns a crappy guess into a better guess, which is purely mathematics, and why quantum computers make that fast, which is where the physics comes in. It all starts with a big number, n, that you'll need to find the factors of to break into some encrypted data. If you don't know what the factors are, which you don't, you can make a guess. Just pick some number g that's less than n. We actually don't need the guess to be a pure factor of n. It could also be a number that shares some factors with n, like how 4 isn't a factor of 6, but shares a factor with it. Numbers that share factors are okay because there's a 2,000-year-old method to check for and find common factors. It's called Euclid's algorithm, and it's pretty darn efficient. All this is to say that to find a factor of n, we don't have to guess a factor of n. Guessing numbers that share factors with n is okay too, thanks to Euclid. And if Euclid's algorithm found any shared factors with n, then we'd be done. You could just divide n by that factor to get the other factor and break the encryption. But for the big numbers used in encryption, it's astronomically unlikely that any single guess will actually share a factor with n. Instead, we'll use a trick to help transform your crappy guess into a pair of guesses that are way more likely to share factors with n. The trick is based on a simple mathematical fact. For any pair of whole numbers that don't share a factor, if you multiply one of them by itself enough times, you'll eventually arrive at some whole number multiple of the other number, plus 1. That is, if a and b are integers that don't share factors, then eventually a to the p will be equal to m times b plus 1, for some power p and some multiple m. Unfortunately, we don't have the time to get into why this is true, but hopefully a few illustrations can at least give you a feeling for it. For example, 7 and 15. While 7 squared isn't one more than a multiple of 15, and neither is 7 cubed, 7 to the 4th is. Or take 42 and 13. 42 squared isn't one more than a multiple of 13, but 42 cubed is. This same kind of thing works for any pair of numbers that don't share factors. So, for the big number n, and your crappy guess, g, we're guaranteed that some power of g is equal to some multiple of n plus 1. And here's the clever part. If we rearrange this equation by subtracting the 1 from both sides, we can rewrite g to the p minus 1 as g to the p over 2 plus 1 times g to the p over 2 minus 1. You can multiply that back together to convince yourself that it works. And now we have an equation that almost looks like something times something is equal to n, which is exactly what we're trying to find. Factors of n. These two terms are precisely the new and improved guesses that Shor's algorithm prescribes. Take the initial crappy guess, multiply it by itself p over 2 times, and either add or subtract 1. Of course, since we're dealing with a multiple of n rather than n itself, the terms on the left-hand side might be multiples of factors of n, rather than the factors themselves. Like how 7 to the 4 over 2 plus 1 is 50, and 7 to the 4 over 2 minus 1 is 48, neither of which is a factor of 15. But we can find shared factors by using Euclid's algorithm again, and once we do, we'll have broken the encryption. So, is this all Shor's algorithm is? Why can't we use this to break encryption right now? Where's the quantum mechanics? Well, indeed, there are 3 problems with these new and improved guesses. First, one of the new guesses might itself be a multiple of n, in which case the other would be a factor of m, and neither would be useful to us in any way. And second, the power p might be an odd number, in which case p over 2 isn't a whole number, and so our guess taken to the power of p over 2 probably isn't a whole number either, which is no good. We're working with integers here. However, for a random starting guess, it turns out that at least 3/8 of the time, neither of these problems happens, and g to the p over 2 plus or minus 1 does generate guesses that share factors with n and break the encryption. This is worth repeating. For any initial guess that we make, at least 37.5% of the time, our guess to the power of p over 2 plus or minus 1 will lead to a factor of n, decrypting the garbled message, which means we're 99% likely to break the encryption with fewer than 10 guesses. However, problem number 3 is the big one. Remember, to turn a crappy guess into a good guess, we need to know how many times you have to multiply our guess by itself before we get a multiple of n plus 1. And for a normal computer, the act of finding that power p takes a ton of work and time. It's not hard for small numbers like 42 and 13, but if our big number is 1,000 digits long and our crappy guess is 500 digits long, then trying to figure out how many times you have to multiply our guess by itself before you get some multiple of the big number plus 1 takes a ridiculous amount of trial and error on a normal computer. More effort than it would have taken to just factor n by brute force in the first place. So, finally, this is where quantum mechanics comes in and speeds things up an insane amount. Unlike a normal computation, which gives only one answer for a given input, a quantum computation can simultaneously calculate a bunch of possible answers for a single input by using a quantum superposition. But you only get one of the answers out at the end, randomly, with different probabilities for each one. The key behind fast and reliable quantum computations is to set up a quantum superposition that calculates all possible answers at once, while being cleverly arranged so that all of the wrong answers destructively interfere with each other. That way, when you actually measure the output of the calculation, the result of your measurement is most likely the right answer. In general, it can be really hard to figure out how to put any particular problem into a quantum form where all the wrong answers destructively interfere, but that's precisely what Shor's algorithm does for the problem of factoring large numbers. Well, actually, it does it for the problem of finding the power p. Remember, at this point, we've made a crappy guess g, and we're trying to find the
Okay, I'm going to stop it there, but I will put this link in there. I just find this really interesting, and what are we going to do about encryption once quantum computers are, more available? It is very scary, right? That we will have to come up with new solutions to Shor's algorithm. So, you all have a great weekend, and we will talk to you soon.